Hello, my name is Cody Scarborough, and I am a graduate student at the University of Michigan. My advisor is Dr. Anthony Gerbic. In this presentation, I will be going over a novel electromagnetic boundary condition, which can be used to simplify the analysis of traveling wave modulated structures. Traveling wave modulation, or TWM, is a form of space-time modulation in which the time dependence of the modulated parameter has a delay that varies linearly with space. Recently, TWM has been used to achieve electromagnetic effects such as beam steering, frequency conversion, amplification, and non-reciprocity. In practice, TWM is often accomplished by applying staggered modulation signals to a spatially discrete array of unit cells, referred to as spacetime pixels or stixels. We call this form of modulation spatially discrete traveling wave modulation, or SDTWM. Solving an SDTWM problem is complicated by the fact that there are several time-varying stixels within a spatial period. Even if the spatial periodicity is invoked to reduce the domain of the model, we still have to solve for the field in several time-varying stixels simultaneously. Here we present a boundary condition for SDTWM structures, which can be used to determine the fields throughout space given the solution in just one stixel. The boundary condition is referred to as the interpath relation, and can be derived by applying the Floquet theorem and phase matching conditions on a spacetime grid. The interpath relation can be interpreted as a modified spatial Floquet boundary condition, where a frequency harmonic dependent phase delay induced by the modulation is added to the standard block phase delay across the stixel boundaries. This relation implies that the solution within a single stixel determines the fields throughout space. When applied to numerical analysis techniques, this saves on computational resources and thus often monetary resources. In our group, we have written a method of moments-based solver to compute the field scattered by a two-dimensional SDTWM capacitive sheet on top of a grounded dielectric substrate. This structure has been shown both numerically and in experiment to produce useful electromagnetic functions like beam steering and subharmonic mixing. In fact, this particular case of SDTWM is capable of achieving beam steering and subharmonic mixing simultaneously. Computing the scattered field in this example without the interpath relation would have required about 2 terabytes just to store the final interaction matrix. Using the interpath relation, we dropped this requirement down to just 187 megabytes. As research into space-time modulation evolves, the ability to simulate complex structures prior to fabrication becomes increasingly important. It is our hope that the interpath relation simplifies both the theoretical and numerical analysis of spatially discrete traveling wave modulation.